Okay, so before we begin today, let me point out first we're going to take a small diversion into this paper by Chris Doran and Anthony Lazenby. Now, Mr. Doran is like a big name in this field. I think he was a student of the man who actually has been championing this for years and years, and he's written a lot of really good papers on geometric algebra. And this is a wonderful paper. You can get this on the web. We're going to start in part 2 just because we're interested in his review of relativistic physics, right? There's a lot of great stuff in part 1 about three-dimensional geometric algebra and its application to elementary physics, and I was really tempted to go through some of that. But because usually you do that. You do three-dimensional geometric algebra and physics first, and then you do this. So we're kind of biting off a much harder problem, but I really like the richness of the space-time algebra, so I'm happy with that. But we're going to spend a little bit more time. The paper we're doing now, as good as it is, kind of all the entire body of relativistic physics in it, I think, is just what we've already done, the Lorentz transformation. So I want to do a little bit more. But before we begin, I want to do a little bit of errata from the last lecture. We wrote down this formula here in the last lecture, and remember, V is a bivector, right? It's got this little arrow up there looking like a vector, but of course it's constructed of relative vectors, which are bivectors. And we're looking at the space-time product of V and the portion of some other bivector field that is perpendicular to V. So E perp means literally perpendicular to V, right? And then we wrote down this expression here. Now this expression here, where did that actually come from? And the answer is it came from our paper, right? Section 3.52, right? It came from this section of the paper. And here it is right here. And it's worth just reminding ourselves. Now, we discussed this in lecture 17 of this series in great detail. So if you want to go back to lecture 17, somewhere around the first section, we talked just about this. But just to review, the geometric product of two bivectors, f and g, this paper wants us to think of it in these terms. And this is a very functional way of looking at it, right? It's the zeroth order of something they're calling f dot g and the fourth order of something they're calling f dot g plus f, this commutator, or this commutator, this 1/2 commutator of f and g, right? Now notice that this could be written slightly differently. Right? In full generality, this is a geometric product. So this is the zero order part of the geometric product. This is the blade 4 part of the geometric product. This is the blade 2 part. What they're trying to say is they're trying to make it a little bit easier, saying, okay, the blade 2 part of the geometric product is this thing. The blade 0 part of the geometric product is this thing. And the blade 4 part of the geometric product is this thing. And f dot g is not the same as fg, right? This is the geometric product of fg, the zero part of it. It's sort of just pure notation. This is some new thing that they're defining as the dot product between f and g. And that dot product they define right here as the symmetric part of the geometric product itself. Now notice this symmetric part, it's expected to have a blade 0 piece and a blade 4 piece, right? Because this is just, remember, these are defined to be bivectors in the beginning, right? These are, f and g are bivectors. So when you do this calculation, this symmetric piece should have a blade 0 part and a blade 4 part. But over here, when I wrote this down, I kind of implied that this thing only really referred to the blade 0 part. So what's missing is that this should also have a line over here to this, right? And the same rule still applies. Remember, we know that these two bivectors anti-commute because they're perpendicular to one another, and therefore this thing goes away. And so that the fact that this goes to 0 eliminates both of these. So two perpendicular bivectors just end up with a blade 2 piece, okay? Again, a deeper review of this is in our 17th lecture of the geometric algebra subpart of this larger thing that we're calling QED prerequisites. Okay, so with that in mind, our errata, this was all errata. This is done. Yeah, no, 2 R's and 1 T. Okay, so let's now carry on and examine this paper. So they begin by just saying, okay, why is this all important? And ultimately, it comes down to rotors in this algebra provide the simplest means of performing Lorentz transformations. So they just go right in there and say, look, this is the simplest means of performing Lorentz transformations. So they're just hitting for the fences right here. And okay, I'm not going to argue the point. It's not like I do Lorentz transformations in every possible way. And it certainly does seem pretty simple once you learn how rotors work. So good on the geometric algebra. They start by saying, okay, this is an algebra for space-time. And just this title is bold because seeking a mathematical structure of pure space and time and rotation, that's sort of been a big deal for a lot of mathematics. I mean, all of that whole drama with quaternions and, that you may not be aware of the history, the battle between Gibbs and, who was the guy who invented quaternions? Was it Hamilton? Hamilton, right? This Gibbs-Hamilton battle over how we're going to write down vectors, right? Where Gibbs ultimately wins this battle completely. I mean, totally wins it. Hamilton's just gone. And it's actually good reason, right? Like quaternions were very close to being quaternions were like space-time adjacent. They weren't quite right. And we could explain why, and the geometric algebra illuminates why. In particular, quaternions kept thinking about rotation along axes when the real thought if it was rotations through planes. And that distinction screwed up a couple signs that Hamilton had to deal with, and it just was kind of a mess. So Hamilton loses that battle, but all of a sudden, here these guys come back and they say, okay, we've got it. We've got an algebra for space-time. Gibbs, hold my beer. Hamilton, sorry, close but no cigar. This is actually where you should have been. And so that title, there's a little boldness in the title, but it's fair, right? I mean, they come over 100 years later to do this. So sure, we're armed with more tools, and we put it all together, standing on the shoulders of giants. There it is, the algebra of space-time. So they go on, and first they say, okay, this is sort of the section that describes the algebra straight up. First, the metric is what's important, right? We know that all of these geometric algebras, you have to stipulate what the metric is going to be for the algebra. And in this case, notice that they're using a mostly minus convention, right? They use the particle physics choice of signature, they call it. And that's embodied down here. Now, we would have written this as gamma 0 squared equals minus 1, and we would have said gamma I dot gamma j equals delta ij. That was the prescription we used in the other paper. All these, and then this part here would have been minus plus plus plus, right? And look, if you're going to study geometric algebra, you just got to be used to the fact that different papers have different conventions, obviously different symbols, and there's not, in the end, as far as space-time algebra is concerned, this choice of signature doesn't manifest itself except during the calculations, but the answers all end up being the same. I do recall somewhere somebody explaining that there is some difference in the choice of signature between some aspect of the algebra. I've never tracked that, and I don't know what it is. If anybody knows that, please leave it in the comments. I'd like to find out. So then they talk about the bivector algebra. Remember, this is the part 2 of a paper. So geometric algebra already. They want to point out that the bivector algebra of the space-time algebra, right? This bivector algebra of the space-time algebra is an important thing to know. So they start by saying, okay, we're going to pick vectors that are orthogonal, right? That's what that statement means. If we're taking two vectors A and B, where A dot B is 0, and we're asking ourselves, what is the square of the bivector of those guys? And so this isn't hard for us to do. We know this material, but we're going to review it right now just by skimming through this page, catching ourselves up with Doran and with this particular paper, with Doran's paper. And knowing that A dot B is 0, what that forces us is to review the point that the geometric product of two vectors is the symmetric part plus the anti-symmetric part. The symmetric part is 0, therefore the geometric product is the same as the wedge product, which allows us to translate from from the far left to the second to far left. And then we know that because they are perpendicular, we know that these guys anti-commute, because this, by definition, anti-commutes. And so that allows us to flip this and introduce this sign, and then we're left with a squared, b squared. So now it's just a question of which of these E0, EI, or I guess E1, E0, E1, E2, and E3, which ones of these do we substitute in here to tell us the final sign? Is it +1 or -1? And in this paper, of course, if we use EI and EJ, because I and J are never 0, we're going to get a -1 for the square of the bivector. And if we get EI, if E0 is mixed in there, we're going to get a +1. Now notice the fact that we get the -1 squared for this and the +1 for this doesn't depend on the metric, right? If we used our metric, this would be minus times plus, which is a minus. And if we use their metrics, it's minus times minus times minus, which is a minus. And the same thing would be true here. If we used our metric, we'll get minus times plus times minus, which is a plus. And if we use their metric, we get a minus times minus times plus, which is a plus. So this does not depend on the metric, right? The metric doesn't care about this. And that's really important, right? Because the relative bivectors have to square to 1, because when we form the rotor of the relative bivector, those represent our boosts, as we learned in the last lesson. So the Taylor series there has got to have an object in the exponent that squares to 1, that isn't 1 itself, to give us this hyperbolic cosine and hyperbolic sine, which they write as CH and SH, right? So that's really cool. I really, really like this. Of course, if this was EI, EJ up here, like E1, E2, or E2, E3, this would have ended up as regular cosine and regular sine. Okay, and then they move on and they define the pseudoscalar. The pseudoscalar is always this straight-up geometric product of all the basis vectors. And so there you have it. There's no distinction between this pseudoscalar and the one we use. The metric is irrelevant in this definition. What is important is that they write, we still assume that E1, E2, and E3 form a right-handed orthonormal set as usual, right? So remember, this is sort of these are these spatial directions, and E0 is the time-like direction. So E1, E2, E3 form a right-handed orthonormal set, just as in three-dimensional regular geometric algebra, or three-dimensional vector algebra for that matter. Then they go on to point out that I is grade 4. This is the reversion of I, E3, E2, E1, E0. But because it's grade 4, the reversion is actually equal to I. So it reminds us of that. And therefore, it shows us that I squared is -1. And you can go through this. Again, the fact that the metric is different does not change this point. Multiplication of a bivector I results in a multivector of 4 minus 2 is 2. So I multiplying a bivector times I gives you a new bivector. And they like to point out that I commutes with bivectors, right? I commutes with bivectors. That's what this is to represent. And you can just do the calculation to get all of these commutation relations, which we looked at before. So we know how these duals work. Now, if they define B sub I as EI, E0. So this notation links up with our notation. We would write sigma I equals gamma I, gamma 0. That's how we would have done it. So they have this B in there. And then we deal with we deal with this little box. So here they wanted to find something that it's looking like a cross product between these two bivectors. Bi is a bivector, Bj, these are the relative bivectors. Now they haven't used that language. They don't call this the relative bivector yet. They might later, but right now they're just calling it, we're defining B. But this to us, these are the relative bivectors. And they had defined this interesting cross product between two relative bivectors to be epsilon ijk and ibk, which is interesting because in our last paper, we kind of worked pretty hard to get it so that relative bivector I cross relative bivector j equaled epsilon ijk relative bivector k, I think, right? We definitely had E1 cross E2 equal E3, and E2 cross E3 should equal E1, right? We had it so that these cross products for these relative bivectors had the exact same mathematical structure as your standard, I cross J, I hat cross J hat, right, equals K hat from regular Gibbsian math. But that's not what's going on here, right? What's going on here is you've got this extra I in there. So we know that the dual of BK is going to be, the dual of a relative vector, which is what these B's are, is going to be one of these space vectors. So this doesn't really agree with our previous work. And then they put down all three of these possibilities. They have the cross product between the relative vectors, the cross product between the duals, and then the sort of interdual relative cross product. And so they have these three formulas. These are interchanged by duality transformation. So they have that's for the trivector. So let's forget this for a second. Let's figure out what's going on here. Why is their cross product different from the one that we studied? And I've actually prepped this out. And the reason is they have defined this cross product to be, let's see, okay. They've defined the cross product to be this thing right here. I've blown up a section of their paper from much, much earlier where they define these things. And they say that A cross B is simply this 1/2 commutator, right? That's their definition of the commutator product. And if you use that definition of the commutator product and you do all the calculations with how they define B, right? With how they define B right here, you end up with this, right? They're consistent with themselves. Our paper, on the other hand, defines the bivector cross product to be the same commutator with that, there's that little 1/2 hidden in here. But look, they put on an inverse I here. We put on an inverse I in our work. And that inverse I is really important because it really makes the connection between these bivectors. When these bivectors are the relative basis bivectors, that inverse I allows us to literally say that the cross product is just the same as the classic cross product. In fact, actually, he writes, after we introduce the relative three vectors, it will become clear that this cross product is completely equivalent to the traditional three-vector cross product, again, motivating this choice of notation. So they were motivated to add this I inverse in here, which exactly compensates for this I, for this I right here. That I will end up basically going away, and then these cross products will be defined without that I, and it'll look just like the regular vector cross product. So that's an interesting thing. You got to really stay on your toes with the notation in this phase of the life of geometric algebra where these things are not... Actually, that's generally true for almost all mathematics anyway. Sometimes you go to older books, or sometimes, authors have different preferences. I mean, it's not just because this is relatively young, and I don't even think it's fair to say that geometric algebra is all that young anymore anyway. But anyway, so keep that in mind. So Doran has that different definition of the bivector cross product. Okay, what next? The spacetime algebra. In many applications, we are interested in physics in a single preferred orthonormal frame. We define the frame by gamma mu. So now they're switching into gamma mu. They're saying, okay, we're going to deal with spacetime, and we always like to use gammas because in the end, these gammas are related to the Dirac matrices. Now, how is that relation done, gamma mu, right? Well, first of all, the notation-wise, the Dirac matrices are written with gamma mu, right? Anybody who's done any field theory or even just advanced relativistic quantum mechanics without field theory, anybody who's ever touched the Dirac equation has seen these gammas. And they are always understood to be matrices. And the point, ultimately, spoiler alert, is that those matrices form a representation of the space-time algebra. So the space-time algebra, as we've done it, it's just fine to use these little abstract E1, E2, and E3 for the vectors, right? Just give them names, understand sort of what they stand for as far as spatial orientation, and move on. But if you replaced each of those vectors with these matrices, all the math in the space-time algebra would work out the same way because these Dirac matrices are a representation of the space-time algebra. So we like to use that fact, and it's sort of foreshadowing, right? Because we haven't talked about Dirac matrices or anything. But foreshadowing that fact and being familiar, we go with the gamma. And so they now abandon E1, E2, E3, E0, and go with gamma 0, 1, 2, 3. And so then they point out that, okay, you end up with a full algebra that has the scalars, the 4 vectors, the 6 bivectors, the 4 trivectors, which they expressed as left-hand duals of the vectors, and 1 pseudoscalar. Now, just to make the point, if you go back to, this is from the paper that we're actually studying, right? They list the 4 vectors here, but then in their complex version, they have the trivectors are right-hand multiplications by these various by the one blades. So there is a difference there too, right? The other paper has them as left-hand duals. These are right-hand duals. And so there's a difference, right? There's a difference, right? Another distinction between these papers. Okay, and now they go to our sigma definition, right? So they go to sigma. Now, why do they go to sigma, right? What is it about sigma that is important? Why are we all converging on sigma? Well, it's because the Pauli vectors can be used to reflect the three-dimensional space-time algebra, and the Pauli vectors, the Pauli matrices, can be used to represent the three-dimensional space-time algebra. And those Pauli matrices are always written in the notation as in the common notation of sigma. So we're struggling to get the notation of geometric algebra aligned to three-dimensional quantum mechanics and four-dimensional quantum mechanics of Dirac. The three-dimensional quantum mechanics of Pauli and the four-dimensional quantum mechanics of Dirac. They warn us that in the literature, the simple I is often used for the pseudoscalar, but they are worried because they're going to talk about quantum mechanics, or they have talked about quantum mechanics already in, I think, the end of the first of these 2 papers that they wrote. So they don't want to make that confusion. So I is almost always capitalized. In almost all the work I've ever read, the pseudoscalar is always a capital I. And then they talk about the reciprocal frame, which I think we've discussed that already. And then to drive this point home, they point out that the relationship between these vectors are really important. The relationship between these one blades satisfy this rule, which anybody who's familiar with the Dirac matrix algebra immediately sees satisfies that algebra. And if you're studying geometric algebra and you've struggled with the Dirac equation, looking at this is like, wow, that is really interesting. This should be really interesting to anybody who's reading this, because this whole Dirac matrix algebra is just like sitting there inside of the geometric algebra, which in many ways is, geometric algebra is kind of, I guess it's easy, right? I mean, we haven't integrated anything. We haven't done any really, really complex mathematics. It's all almost combinatorics, right? It's like little group theory stuff. And yet there it is. These are the key relationships of the Dirac matrix algebra just sitting there. So it's very profound, right? So they point out, it must be remembered that the gamma mu are basis vectors. They're not a set of matrices in something called isospace. And that's a good point, right? I like the way they say that, because when you study this in physics, when you study the Dirac matrices in physics, they do introduce this weird thing like isospace. That's sort of an old term. I don't see it that much used anymore. But in the original days, they were trying to emphasize that there's these Dirac matrices generate rotations in this weird thing called isospace that's not space but has the same kind of mathematical structure in some ways, and it's this weird abstract thing that clearly is an ad hoc concept. But now you don't even have to worry about it. It's just literally built into an algebraic structure that the only significant contact with real physics is through the metric. And once you have that metric and the notion of geometric algebra, this appears just as a mathematical property of things, and you don't have to think about an isospace. So they like to point that out as evidence that this is better. We've eliminated this idea that nobody really understood anyway, right? Okay, so what next? Okay, so now we I feel like we get into the meat of this a little bit more. We're going to talk about x of lambda describes a curve in spacetime. So we're now talking about world lines. So now we can actually introduce, just to understand how this guy actually manifests itself, we can actually draw a bit of a coordinate system. And this up here would be the gamma 0 axis, and then we could have this as any of the gamma spatial axes. We'll go with gamma 1, right? Or gamma 1. And the idea is that you can collect a bunch of points inside this, these on this plane between x0 and x1, and you can say that the coordinates of any spot on that plane, the coordinates of any point on that plane is going to be x of lambda, where lambda is some parameter that lambda equals 0 here, and say, lambda equals 1 there, right? So that's the limit of our interest, where lambda starts at 0 and lambda starts at 1. And lambda we might want to call the proper time. Sometimes if we call it the proper time, we would convert it to tau. In fact, I think they do that right here in a moment. So why don't we just do that? Why don't we just go right to tau? Well, no, it says lambda here, so we'll stick with lambda. But the point is at this spot, we're really talking about a set of coordinates. We're talking about x0. Well, let me just do it the way it would be done in relativity. x0, x1, x2, and x3. And that refers to a point in space-time that is represented by a vector, and we could call that vector x, or a one blade, which would be x0 gamma 0 plus x1 gamma 1 plus x2 gamma 2 plus x3 gamma 3. So the idea is that this vector right here that I wrote down represents this spot in space-time, right? This is the time part, and this is the space part, right? And this is a four-dimensional object, meaning it's moving through a four-dimensional space-time, of which I've eliminated 2 dimensions. And I said, okay, pretend it's not moving in the x2, x3 dimensions. x2 is 0, x3 is 0. Whoops, it looks like that x3 needs to be made up, right? And it's moving in this fashion, right? And if the scale is right, we know that there's this 45-degree line that goes off here that separates space-like, right? This is all space-like movement, and this is time-like. up here, right? Anything above this. So that's why this line can never slope more than 45 degrees to keep motion purely space-like. And, but that's what x represents, right? That's what x represents. X is this line, and lambda is some parameter along the line that should always increase, and as it increases, you just move in this line. And x prime is the tangent vector to this curve, right? So at any point, you could blow up a tangent vector, like right here, for example, and that is what x prime represents, and it's the partial derivative of x with respect to lambda. That's how you calculate x prime. So presumably, you would have a formula for x lambda. Just to be really clear on how this all works, right? You should have x of lambda is some formula which gives x0 of lambda, gamma 0, plus x1 of lambda, gamma 0, plus x2 of lambda, not gamma 0, gamma 1, gamma 2, plus x3 of lambda, gamma 3. So this of lambda, is for each component, right? And that describes the motion of this curve, which usually reflects the motion of a massive particle, right? The way I've drawn it so far. So the presumption is you know what these formulas are. These are known formulas, right? And also, importantly, is you know what frame of reference you're in. You know what the time-like vector is. So if you're motionless in this frame of reference, all these guys are 0. Well, I should say when you calculate this derivative, all of the derivatives of those guys will be 0. But you could presume, just say x1, x2, x3 is 0, and they don't change. So it's motionless, and the only movement you have is in time, right? And so x0 of lambda would presumably be 1, right? It would be one movement in time. So, or some constant number. And the point being that x0 prime should be normalized, so its square is equal to 1. We'll see that in a moment, actually. But that's the nature of what this is talking about, right? This formula here, you know the x lambda, and I just told you how to break out x lambda into its parts. And so you know that, so this derivative can be calculated. If you know what x lambda is, you definitely can calculate this derivative. And then they point out, okay, we're always considering that the square of x lambda is greater than 0 because we want to talk about time-like trajectories. Those are the ones of massive particles, and that's what we care about the most. Space-like null trajectories are also important, but we're going to focus right now on time-like trajectories. So they want to introduce the preferred parameter. So they're now saying whatever lambda was here, change it so that so that dx d lambda, right? This is shorthand notation for partial x of tau. We're going to change it to tau, partial tau. We want that to always be such that this thing is going to be what we're going to call v, right? Which is x dot or x of tau dot. And we're choosing lambda in such a way that v squared is always equal to 1, right? And that can always be done. You can always do that. We've studied that in our special relativity work. But that reparameterization gives us tau becomes the proper time. And v squared always equals 1 is another way of saying that your forward velocity is always the speed of light, right? That's where we're ultimately making contact with the speed of light here. And this, by going with v squared equals 1, that's tantamount to saying that c is defined as 1. So we're in units now where c is dimensionless and equals 1. So with that in mind, what's next? They talk about null vectors, right? And what they're saying is now the problem is parameterizing the path doesn't work as well. And so you have to do some other work. We're not going to be dealing with that right now. Hopefully we'll come back to that. So what's next? Now they're going to talk about these relative vectors. And this is their version of the description of how these relative vectors work. So let's have a look. So they begin with supposing we are an observer at rest in some inertial frame, right? That doesn't mean we're at the origin, by the way, right? If the inertial frame is got its gamma zero here, you don't have to be sitting there to be at rest. You could be sitting there and being at rest, but your motion is all in the gamma zero direction. What's interesting, I just noticed, is that despite the fact that they had a shot at going back to the gamma terms, they actually now have reverted back to the E's. And so these E's are still the four-dimensional spacetime algebra basis vectors. They walk away from the gammas. They introduced them and then walked away from them. I'm not sure what's up with that. So now we're living with E0, E1, E2, and E3. So, but the point they say is that our fore velocity is V. The inertial frame generated by the unit time-like vector V and the frame of rest perpendicular to V. So the rest vectors are E sub I, right? That's the spatial parts, and they're all perpendicular to the velocity. That's what rest basically, well, that defines the orthonormal frame, but they have to be perpendicular to V for everything to be orthonormal. And so we define E0 is defined as V. So we know our vector V is how you define this inertial frame, and we assign V to E0. That's how they're doing it. The other paper didn't bother with this step. The other paper just said, look, you're in the frame, gamma zero is your frame. That's the inertial frame. It's defined by gamma zero, and period. So that's kind of an interesting choice. But I think there's a decent reason for it. They're trying to be a little more general in this paper. So the general event, right? Remember, an event is just a point in space-time. Don't let this word screw around with you. An event is simply a thing that can be written down as x mu gamma mu, which is a single point in space-time. And a whole string of events that tied along a curve is a curve, right? Where this becomes a function of some proper time tau, just like we described a moment ago. And so your general event, oh, there it is, right there, right? That's just what I wrote. But they have now t, they're giving up x0 for t, right? So this is physicsy, right? The other paper, they got to the point mathematically. Now we're kind of making contact with physics as we've always understood it. You know, we have time instead of x0. We split it up into a time part and a space part, right? So we're going to see this in this paper. We get a lot more of just this classic relativistic physics stuff. So that's how our general event is decomposed, and the time coordinate is this vector dotted into E0, right? It's the dotting into E0 is going to kill all of these because EI dot E0 will always be 0. E0 gives us 1, and so because E0 gives us 1, we end up with the time coordinate left over. But notice, because we are at rest in this frame, our velocity can be substituted for E0. So the velocity and E0 are the same, and they make this substitution right here. Now the spatial coordinates, it looks a little different because here in the spatial coordinates we use the reciprocal basis, and that is because of this negative sign, right? So we want the ith coordinate to be E dot with the reciprocal basis. So this is a notational difference that happens between the two. Notice this is the regular basis here, and this is the reciprocal basis. And that'll just pull out the vector without the sign. So suppose now that the event is a point on the world line of an object at rest in our frame. The 3D vector to this object. So this is what they're going to call the 3D vector to this object. And this goes back to some very simple idea here, that if we have our frame and it's gamma 0, gamma 1, and then there's an object that's at rest in this frame. So we'll just say here's the object that's at rest in this frame. So its movement in this frame is like this, right? And it's got a velocity, and the velocity, of course, the velocity squared is going to be 1. But that velocity is like this. But the point is at some point, this object is right here. So we can definitely identify that point with a vector, right? But we're just interested in the spatial part of that vector, because that's what they're saying here. They're saying where did they say it? They're saying, suppose now that the event is a point on a world line of an object at rest in our frame. So this is the world line, right? That's the world line. It's at rest because it's vertical, and here is the point along the world line, and we're only interested in the 3D vector to that object. So that would be the way they're describing it right now. That's just this piece, the xi EI part, right? That's this piece, the spatial piece of the position vector in spacetime. And so now they write down this expression. This expression is kind of interesting. It's kind of worth going through. This spatial part, the spatial part of that vector, is ultimately given by the vector wedged with the velocity, geometric product with the velocity. And notice this is a vector, right? This is just a one blade. So this guy here also has to be a one blade. So let's see how this works. So we start just by writing x in its full form, right? And then what we're interested in is this part right here. So I'm going to solve this for just this piece. So I get x, the spatial part is the full vector minus just this time-like piece. So I basically am bringing this part over to the right side of the expression. And then I can break these down, this and this, into components if I wanted to, right? This is the components of the whole vector, right? It's x dot e mu, e sub mu, right, if I wanted to do it that way. And x dot e0, e sub 0. This would be the time-like piece, and that represents this in component form. But ignoring that for now and just moving down, this we substitute e0 for v. And that right there is the statement that we are at rest in the frame, right? We're taking e0 and we're saying our velocity is equal to e0. That's the statement that we're looking for, the spatial part of an object that's at rest in this particular inertial frame. And then we do a little bit of a trick here. We put in VV, right? V squared, which we know is 1. So we can just insert that right in there. And then we can distribute out this V and this V. We can pull that out to here. And we're left with the geometric product of the full-on vector of where this particle is, the geometric product of that with its velocity, minus x dot v all times v. But this geometric, because these are both one blades, right, we know that, xv equals x dot v plus x wedge v. So xv minus x dot v just equals x wedge v. So now we have x wedge v, v. And that's the answer to the problem. And you can also check this. This is several lectures back, I told you to memorize this form. And you discover that it is indeed a one form, right? This is a bivector and a geometric product with a vector. It looks like there should be a 3 form in there. You know right away there won't be because v wedge v is 0. But even if it wasn't, it still doesn't end up being a 3 form. It turns out that there's a formula here that basically returns you in this direction. Okay, so that explains that formula, meaning we've explained this formula. So wedging with V projects out the components of the vector x in the rest frame of V. The key quantity is the spacetime bivector x wedge V. We call this the relative vector, and we write the relative vector x is the full vector wedged with V. So they're defining relative vectors in terms of these velocities here. So it looks a little bit more general than our work. But the relative vector is the vector x wedged with the velocity, the velocity vector. And so with this definition, you have some nice stuff, right? X geometric product with V is x dot v plus x wedge v, but this is the relative vector. So we can write that as x bold. And now we have something that looks a lot like our special relativity, our classic special relativity. And they're very proud to show that if you square x, you can throw in VV, because VV is 1. And so you end up with this expression here, which is just the square of x dot v plus x wedge v. And the only difference is this is v wedge x. And when you flip those two, you pull in a minus sign, so you get t plus x, t minus x, and you get the number t squared minus x squared. So now you have calculated the square interval of the full vector as being t squared minus x squared, which is exactly what you would expect from special relativity. These are numbers, right? These are numbers. And that is the usual result. So that result is literally built into the definition of the space-time algebra, although, to be clear, it's real important to remember the metric is part of that, right? You recover this metric very quickly. What they're basically saying is that the geometric product of a vector is straight up this beautiful number that we would expect it to be, which is the interval length. And that it feels a little bit more organic, because when we write x squared, you don't have to think about the metric too much here, right? Ultimately, if you're going to calculate t squared and you're going to calculate x squared, yeah, the metric kind of comes in with the square of those vectors, but it kind of lives in there automatically, is what they're saying. A little bit of subjectivity there, I think. Okay, so what's their next topic? Their next topic is the even subalgebra. Okay, so each inertial frame defines a set of relative vectors. Okay, so it's good to note that they're now digging into the word relative vectors. So they're back to relative vectors, and then they're back to this notation of sigma and gamma instead of e's. So to simplify things, we take the time-like velocity vector to be gamma 0. So they're getting rid of now v, so they're going to now just say, okay, gamma 0, that's the definition of v. This frame is, the frames is at rest with respect, if you're at rest with respect to this frame, your velocity is gamma 0. That's another way of saying it. If you're at rest with respect to this frame of reference, your velocity is gamma 0. And what algebraic properties do these have? What algebraic properties do these relative vectors have? So let's, okay, well, this is easy. First of all, you say, if the time-like velocity vector is gamma 0, so all of the relative vectors are gamma I, gamma 0, which we already know. Then we have this dot product, which they just define as the symmetric part of the geometric product of sigma I and sigma j. So sigma I is a bivector, sigma j is a bivector. The geometric product, this is the geometric product of sigma I with sigma j. This is the reverse of it. So this whole thing here is the symmetric piece of the geometric product. That we just went through this in the errata, right? And it's delta ij. So that's nice. And that's the way we want it. We want the dot product between two of these relative vectors to just be 1 or 0. We want it to be orthonormal, right? We want it to be orthonormal, and it turns out it's orthonormal. So these guys are orthonormal under this dot product definition. But these act as vector generators for a 3D algebra. What they really should want to write here is a 3D geometric algebra, right? Geometric algebra. And this is an important point. So it's worth a little bit of a digression, and that is to say the following thing. If I were to take this set of sigma 1, sigma 2, and sigma 3 and treat them not as, I don't need to treat them as necessarily gamma I, gamma 0. Let's just treat them as the names of 3 vectors. And then I were to say, okay, sigma I dot sigma j equals delta ij, right? I define the dot product that way. And then I say that these 3 vectors are the basis of a 3-dimensional vector space. And then I go through the whole rigmarole we went through before, where I say, okay, I'm going to define scalars, and I'm going to define the set of all wedge products, right? So I have sigma 1 wedge, sigma 2, sigma 1 wedge, sigma 3, and sigma 2 wedge sigma 3, right? And then I define a pseudoscalar, which is sigma 1, sigma 2, sigma 3. And if I do that, this basically defines the metric, right? The metric is totally Euclidean. And I've defined this wedge product, which gives me the rest of geometric algebra. This whole thing is a three-dimensional geometric algebra, a 3D geometric algebra. And it has geometric products, right? Sigma 1, sigma 2 is still going to be, because they're vectors, it's going to be sigma 1 dot sigma 2 plus sigma 1 wedge sigma 2. And this is going to be the symmetric part, and this is going to be the anti-symmetric part of a three-dimensional geometric algebra. This is not the same as our four-dimensional geometric algebra. This is a three-dimensional geometric algebra. And in this algebra, when we talk about the three-dimensional geometric algebra, these guys here are just blade 1 objects. They're blade 1 objects. Now, we got to these blade 1 objects by working in a four-dimensional geometric algebra, and we discovered these blade 2 objects out there. So the point of the work of this paragraph right here, the one we were just reading, is if we define this dot product this way in the four-dimensional geometric algebra, right, in our space-time algebra, if we define this dot product, we get these delta ij's. And we can now say, well, if we just skip this part and just go right from here to here by definition, they act as vector generators for a 3D geometric algebra, just like I showed. And that 3D geometric algebra is the geometric algebra of the three-dimensional space that is in the rest frame defined by gamma 0. So this gets rid of basically the time movement. And now you're back into your classic Newtonian physics frame. And the volume element, they figure out, okay, in this geometric algebra, you have sigma 1, sigma 2, sigma 3. Turns out that's exactly the same thing as gamma 0, gamma 1, gamma 2, and gamma 3. So what's interesting is that if you were to make a substitution in the 3 space for these four-dimensional or these space-time algebra definitions, you get the same I. You get I again. So the I is the same in both of these algebras. And the algebra of the relative space, so when I say the algebra of the relative space, I'm now talking about this thing. This is sort of the relative space. It's the geometric, three-dimensional geometric algebra, which we're now calling the relative space, if I understand this right. But the pseudoscalar actually operates the same way. So they calculate this for us, which is neither here nor there. I mean, so both relative vectors and relative bivectors are space-time bivectors. A little bit of a confusing statement, right? Because what they're saying here is relative vectors, that's these guys. They are vectors in the three-dimensional geometric algebra of the relative space. They're vectors. They're not bivectors. But then this space also does have bivectors, right? They have bivectors. Sigma 1 wedge sigma 2, sigma 2 wedge sigma 3, sigma 1 wedge sigma 3, and sigma 2 wedge sigma 3. I don't know if those are the bivectors you would choose to be the basis. I just threw them down. They do span all of the bivectors of the three-dimensional geometric algebra. So you have relative vectors and relative bivectors. And what they're saying is the relative vectors and relative bivectors are space-time bivectors. So both of them are represented by space-time bivectors in the four-dimensional, in the 4D geometric algebra, or the space-time algebra. So these guys are bivectors, and these guys are bivectors when referred to the four-dimensional space. But we call them vectors and bivectors. We separate them into vectors and bivectors for the three-dimensional so-called relative space, the relative space. So that's kind of a confusing little paragraph. But the diagram is pretty clear, right? You map these relative, what we were calling relative vectors in the space-time algebra to literal vectors in the three-dimensional relative algebra, and the duals of those guys end up being bivectors in three-dimensional space. So that's what they're trying to say there. And I'm not going to lie, I feel like the paper we did was a little bit cleaner in that explanation. But the reason is this, because we're approaching this, we've never studied this, right? We started all of our work right here. We were a little ambitious. We wanted to get right to electromagnetism and a four-dimensional space-time algebra. We skipped any kind of detailed study of this, which is actually pretty interesting. You can do a lot of quantum mechanics in just this, with just this three-dimensional space-time algebra. And you can imagine, right, if the Pauli vectors live there, you're going to capture spins somehow, probably, which is the suggestion with these sigmas that these guys are going to be like Pauli vectors. So this is an important subject in physics in its own right, and we kind of skipped over it. So this logic that they're using here might seem a little confusing to us because we're not experts on this three-dimensional geometric algebra. But at the same time, what's there to be an expert of? It's simpler, right? We don't even have, all of the metric is Euclidean. They're all plus ones, and you have one less basis vector, so the whole space is smaller. It's got to be simpler, and the geometric algebra rules are all the same. Anyway, so what they're trying to show you is how you take this four-dimensional space-time algebra and it maps onto this relative space, relative spatial, just pure space, and that's the three-dimensional one. And they make the point that this is observer-dependent. And by observer-dependent, they mean you change gamma 0 in here, and that means you change this, and you change this, and these mappings are going to change too. So the three-dimensional algebra that is embedded in a way in these space-time algebra becomes different as soon as you change gamma 0. Everything depends. That's what the observer means. That's what that means. Okay, let's quickly look at these conventions. Relative vectors are written in bold, right? So when they say relative vectors, they're talking about these guys here. They're written in bold, but there's going to be times when we treat them as, we're probably going to spend most of our time treating them as though they live in here. But we still call them relative vectors regardless of whether we're talking about them in here or in here, I think. There's a potential ambiguity here. How are we to interpret this expression, the expression A wedge B? And I can see exactly what they're getting to right here. I'm not even going to read the next line, right? If I write sigma 1 wedge sigma 2, is that supposed to be calculated in the space-time algebra? Or is that supposed to be calculated in the 3D relative algebra, right? In which case, this is a bivector in the 3D relative algebra, but in the space-time algebra, it's the wedge product of two bivectors, right? So let's see what they say. Our convention is that if all the terms in an expression are bold, the dot and wedge symbols drop down to their 3D meanings. Otherwise, they will take their space-time definition. So if all the terms in an expression are bold, we use the 3D meaning. This works pretty well in practice, so we'll try to draw attention to the fact that this convention is in use. Fair enough. In our other paper, by the way, we wouldn't need to worry about this convention because they just don't completely drop into the 3D algebra, or haven't yet at least. Okay, so the next material is starting to do all the examples, and obviously we've gone way long just catching up to where we're at now, so we'll do that next time.